Hello students, in the earlier video we have seen what is Zeeman effect and what are the types of Zeeman effect, and we have also seen the experimental arrangement for observing the Zeeman effect. So you know that application of strong magnetic field will split the spectral line into several components. That is what the Zeeman effect. So in normal Zeeman effect, we have seen that the spectral line component will be split into three components. And in case of anomalous Zeeman effect, a weak magnetic field can even split a single line into several spectral lines. So that is the basic types of Zeeman effect, normal Zeeman effect and anomalous Zeeman effect. Now today we are going to see the explanation of Zeeman effect given by Lorentz on the basis of classical theory. So by studying this explanation, you will understand the principles why we observe this Zeeman effect because of application of strong magnetic field to the spectra of the elements. So let us see this classical theory given by Lorentz. So explanation of Zeeman effect was given by Lorentz on the basis of electron theory. So you know that the electron, according to Bohr model, it is revolving about the nucleus in circular orbits. So in this particular case, if you apply the strong magnetic field according to Lorentz theory, when light is placed in a magnetic field, the motion of the electron is modified in such a way that their period of motion get changed. That means here when you excite certain element and it gives out radiation, for example sodium source or mercury source. So for this particular element, when you apply strong magnetic field to across these radiations, that means the excited state of that element, then in that particular case, you know that the radiations given out by that element, it contains different spectral line, and that is a unique characteristics of that element. Every element has a unique set of spectral lines that we call as a spectra of that element. So when you apply a strong magnetic field according to Lorentz theory, what happens? The motion of electron is modified. So in each of these element, you know that there are certain number of electrons, and these electrons are revolving about a nucleus in different orbits according to Bohr's theory. So the motion of these electrons is modified in such a way that their period of motion get changed. So this is very important. So the basic concept that Lorentz has put forth is based on the electron theory. The revolution of electron, revolving orbit of electron is modified because of the magnetic field. So that was the concept put forth by Lorentz. So if the magnetic field H is normal to the plane of the circular orbit of an electron. So if you assume, suppose this is the circular orbit and the magnetic field is normal to the direction of this plane of the circular orbit, then the electron will be either speeded up or slowed down. So you know that any particular charge particle, when it is in motion, you know that if you apply the magnetic field, there will be a force acting on the charged particle. So electron is a charged particle, negatively charged particle, you know that, and therefore the presence of magnetic field will certainly cause a force acting on the electron. So because of this force, electron will be either speeded up or slowed down. So let us see now what Lorentz has proposed. So if the magnetic field H is in the upward direction and normal to the plane of circular orbit, I have shown this. Suppose this is the circular orbit and this is the plane horizontal plane. You can see this is the horizontal plane here, and the magnetic field H is applied, which is in this direction, upward direction. So it is perpendicular. It is perpendicular to the plane of the orbit. Okay, the direction is shown here is in the upward direction. So if the magnetic field H is in the upward direction and normal to the plane of the circular orbit of an electron, then electron moving in clockwise direction will be speeded up by delta nu. So see here, an electron moving in clockwise direction. Suppose this is the electron which is moving in clockwise direction. So it will be speeded up. So its orbit will be modified. Its orbit will be modified. Its velocity will be modified. So it will be speeded up because of the force acting on it. Because of presence of the magnetic field. So this electron will be speeded up by an amount delta nu. Okay, later on we are going to define this delta nu. So, and if you consider opposite case, suppose the electron is moving in an anti-clockwise direction, this way, the second diagram you can see here, then in that particular case the electron moving in anti-clockwise direction will be slowed down by delta nu. So the motion of the electron will be modified in such a way that it will be slowed down. So the orbit will be modified. Later on we shall see these particular details of delta nu, what is this quantity delta nu, and how the force is either acting towards the source or acting away from the center of this orbit. So in which case the force is acting towards the center or away from the center, that will be decided by Fleming's left hand rule. So we shall see that particular later on. Now let us consider an electron moving in a circular orbit. So according to the Bohr's theory, we have seen that the centripetal force is acting on it, and it is given by F is equal to mv square upon r, where m is the mass of the electron and r is the radius of the orbit, and v is the velocity. So F is this force, centripetal force acting on the electron, which is revolving in a circular orbit. So, but you know that V in a circular motion, you have studied that V is equal to R omega, where omega is the angular frequency, and it is given by 2 pi upon T, where T is the period of revolution, okay, the period in a circular orbit. So this R omega will be equal to 2 pi upon T into R, and you know that 1 upon T is nu, that is the frequency. So 2 pi R into nu. So V is equal to 2 pi R into nu. So therefore F you can modify as m upon R into V square. V is 2 pi R nu. So V square is 4 pi square R square, this nu square. Okay. So one of these R will get cancelled. So what is remaining is 4 pi square m R nu square. Okay. So suppose this is equation number 1. We will need this equation later on. So we have given a number 1. Just remember it. Okay. Now let us go ahead. So if the magnetic field is applied in a direction which is perpendicular to the plane of the electron orbit, as I have shown in the earlier slide, the circular orbit and the direction of magnetic field is in the upward direction and it is perpendicular to the plane of the orbit. Okay, so the additional force H-E-B acts on the electron. So because of the presence of magnetic field which is in the upward direction and perpendicular to the plane of the electron orbit, there will be an additional force acting on the electron, and that is given by H-E-V, where H is the magnetic field intensity. Okay, E is the charge on electron and V is the velocity with which the electron is moving in the circular orbit. So using this V, that is equal to 2 pi R nu, we already defined this velocity. So therefore the additional force of an electron due to magnetic field is equal to H-E-V. You just substitute V, that is H-E 2 pi R nu, H-E 2 pi R nu. So that is the additional force acting on the electron. So then you can, according to Fleming's left hand rule, as I have mentioned earlier in the earlier diagram. So if you apply the Fleming's left hand rule here in those particular diagram, the direction of this force will be towards or away from the center if the motion of the electron is clockwise or anti-clockwise respectively. That means here when the motion of the electron is in clockwise direction, then the force will be towards the center of the orbit. And what will happen if the force is toward the center? The orbit will be contracted. That means the motion of the electron will be speeded up. And second thing, if it is in anti-clockwise direction, then it will be, the force will be away from the center. So the orbit will expand. The orbit will expand and the electron will be slowed down by a certain amount. So the additional force is towards the center of the atom. The orbit contracts and the frequency of the rotation will increase. In that particular case, the frequency will increase. In that particular case, frequency will increase because the orbit will contract here. The orbit will contract. And second thing, if additional force is away from the center of the atom, the orbit expand and the frequency of the rotation will decrease. So this increase or decrease in frequency is the cause for splitting. Okay, so increase in frequency and decrease in frequency, that will be decided by the clockwise or anti-clockwise motion of the electron. So you can say here the additional change or additional, because of this additional force. So total force you can say F plus or minus He2 pi r nu. Okay, what is He2 pi r nu? So that is the additional force acting on the electron because of the what we can say presence of magnetic field. So the earlier force plus, earlier force means the centripetal force. Okay, so centripetal force we have defined. So if you multiply this, if you add this F plus or minus He2 pi r nu, that will be the total force, and that will be equal to 4 pi square mr nu L square. Okay, 4 pi square mr nu L square. So suppose this is equation number 2, where frequency of the orbit is nu L, So that will be the total force. Now using equation 2, in equation 1, we can get here this total force you can see here. Okay, and the earlier force that we have defined, that is 4 pi square mr nu square. So if you rearrange the term, you will get 4 pi square mr in bracket nu L square minus nu square, that is equal to plus or minus He2 pi r nu. Okay, this is additional force. So if you take this force on this side, which is simply 4 pi square mr nu square. Okay, and this is nu L square. So 4 pi square mr you can take common. So nu L square minus nu square, and that will be equal to this term, additional force, plus or minus He2 pi r nu. Okay, so therefore nu L square minus nu square, that is equal to plus or minus He nu upon 2 pi m upon 2 pi m. Okay, so this nu L minus nu, so you know that a square minus b square, you can just use the formula here, that is a plus b into a minus b. So nu L minus nu into nu L plus nu, that is equal to plus or minus Hev upon 2 pi m, Hev upon 2 pi m. Okay, so you know that if nu L is approximately equal to nu, so very small change in the frequency. So what will happen if you assume that nu L is approximately equal to nu? So nu L plus nu here, that will be approximately 2 nu. Okay, that will be 2 nu, and nu L minus nu, you can say that will be a very small change, that is d nu. Okay, that is d nu, and therefore left hand side will become nu L minus nu, according to this approximation, nu L minus nu, that is d nu, and this is 2 nu. Okay, nu L plus nu, that is 2 nu. So d nu into 2 nu, that is equal to He plus or minus Hev upon 2 pi m. Okay, so therefore d nu, that will be equal to, sorry, this is nu actually, He nu upon 2 pi m. So what will happen, this nu and this nu, that will get cancelled. So d nu is equal to plus or minus He upon 4 pi m, He upon 4 pi m. So this is equation 3. So d nu is important for us. So what is the change in frequency because of the application of magnetic field? Either plus He upon 4 pi m or minus He upon 4 pi m. That will depend upon the motion of the electron, whether it is clockwise or anti-clockwise direction. But you know that nu, that is frequency, is given by the formula C lambda. Therefore d nu is equal to minus C upon lambda square into d lambda. So if you differentiate this, d nu will be equal to minus C upon lambda square. This is the differentiation of C lambda into d lambda. So now you can just convert this relation in, this is in terms of frequency change, d nu. If you want this relation in terms of the wavelength change, then you can just convert it into in terms of lambda. Therefore we have substituted nu is equal to C lambda, and just by differentiating, d nu will be equal to minus C upon lambda square into d lambda. Okay, so d lambda is equal to, if you substitute this quantity here, by just rearranging the term here, d lambda will be equal to this minus lambda square upon C into d nu. Okay, so that is the relation here. Now you can just substitute here d lambda. So using d nu from equation 3, we get d lambda is equal to plus or minus lambda square upon C into He upon 4 pi m, and this is the required relation, final relation, that gives you the two additional lines, once plus lambda square upon C, He upon 4 pi m. D lambda represents the small change in wavelength. So one spectral line, that will be divided into three components: the original line, then other line which is having slightly higher wavelength, that is plus lambda square by C, He upon 4 pi m, and the third line that is having slightly less wavelength than the original line, that is minus by an amount minus lambda square by C, He upon 4 pi m. So this explanation is very important. Lorentz classical theory, that helps us to understand why a single line, when you apply a magnetic field, is splitted into three components. When a single line will split it into three components. So it depends upon what? So E is charge on electron, M is mass. So both of these, if you assume them to be a constant, then H, magnetic field strength, that will decide the amount by which there will be a splitting of the lines. Okay, the change in wavelength, that will be decided by the strength of the magnetic field directly. So lambda is the wavelength of original line, and d lambda is the change in wavelength. So this is how the explanation given by Lorentz according to the classical laws of physics. So this is very important. The normal Zeeman effect, when we observe in case of any particular element, a single spectral line is split into three components. The original line, one line having slightly higher wavelength, so this higher wavelength is d lambda is equal to plus lambda square by C upon into He upon 4 pi, and other line, third line, having slightly lower frequency, minus lambda square by C into He upon 4 pi. So this is very much explained, correctly explained by Lorentz by using classical laws of physics. In the next video, I am going to explain the quantum mechanical explanation for this Zeeman effect. One can understand why we get such three lines in normal Zeeman effect. A single line is split into three lines. So that can be also understood on the basis of quantum mechanical theory.